The main thing to remember, I think it was mentioned in the previous section, is that the atomic nucleus is very, very, very small, very, very small. And the reason it's very small is because the fundamental force that holds together the particles that make up that nucleus, we call it the strong nuclear force, acts over a very, very short range. And that range is something like 100 million millionth of a centimetre. What that means is that force is very, very strong, and that extra binding or strong force between, if you like, the sticking glue between the protons and neutrons in the nucleus adds a little bit of extra energy to the system. So listeners will be familiar with the only equation that sort of matters in physics, which is the famous Einstein one, E equals mc squared. And that idea is that energy and mass are sort of two interchangeable products, two sides of the same coin. And the idea is if you've got a very, very tightly bound, stuck together nuclear system, some of the mass is converted into what we call binding energy. Not very much, only about probably less than 1% of the total mass of the nuclear system is binding energy. But if we can release that, and that's what happens in nuclear fission, we can release an enormous amount of energy that's sort of held together and compact in there, a little bit like bursting a balloon by pricking it with a needle.
And in this instance, what's the nuclear prick that you use to burst that nuclear balloon then?
Well, it's the particle that was just mentioned earlier. It's the neutron, and a very interesting particle, the neutron. So it wasn't discovered, as the previous gentleman said, until 1932. That was almost 30 years after the discovery of the nucleus itself. And the reason it's hard to discover or hard to find is because it has no charge. There's another interesting thing about the neutron in that if you have a neutron on its own, a sort of lone, standalone neutron, it only survives as a neutron for about 10 minutes. It naturally radioactively decays. But when it's bound inside an atomic nucleus, it can basically live forever. So the little bullet, the little magic bullet that tickles the specific radio or the specific chemical element that we use in most nuclear reactors to cause nuclear fission, which is uranium, is processing a very, very slow bullet of this neutron material, and it's just captured by the uranium nucleus, and that tiny capture causes the nucleus to be unstable, to wobble a little bit and split up into two smaller fragments, releasing some of that binding energy. And the amount of binding energy that's released is about 1,000,000 times more per energy release than you would have in a chemical reaction like coal burning, and that's why nuclear power is so efficient.